This video will be talking about the concept of chemical equilibrium. I'm going to use a very similar example to the N2 and O2. I just changed it to H2 and I2 because that's one of the examples the books use. Again, it's just going to be a collision of these two molecules to form the product where the bonds are between hydrogen and iodine rather than hydrogen and hydrogen and iodine and iodine. Okay, so we have a very similar picture. We have an energy requirement for H2 and I2. And we must put this much energy in between these two molecules to form these two molecules. Okay, now we have a container with both hydrogen iodine and hydrogen iodide. Now we have to ask ourselves, can another reaction occur if I have two HI molecules colliding like so? Will it reform this bond and this bond, in which case you get hydrogen back and iodine back? And the answer is yes. Okay? So if you have two molecules, H2 and I2, with enough energy to collide to get over to make the products, well, these are in the same system. They also have energy because they'll have a certain temperature and there will be a distribution of kinetic energies. Well, if two HIs collide with enough energy and in the right orientation where the hydrogens are together and the iodines are together, it only needs this much energy. Okay? It's actually a lot easier to go for the reverse reaction. Okay? So what a chemist does is write down, here's what happens. I can take two HIs, and when they collide, I'll get H2 and I2. And this reaction should actually be faster than this reaction because this reaction requires a lot of energy. This one does not require so much energy. Okay? A lower barrier to get over. So it actually, you'd expect this to happen a lot easier. So what will happen as a reaction occurs? If there's only molecules on this side, there's only one way the reaction can occur, and that's for them to collide to make HI. HI cannot collide because we're not starting with any. We have none. Okay? So as you start, you're out of equilibrium if you have reactants only. You start to make a few products. Okay? And those products are there, and they will occasionally collide, not frequently because there's not very many and they don't meet each other very often. But as this reaction proceeds forward, there's more and more HI molecules. And that means there's more and more collisions between two different HI molecules, and there's more and more reverse reaction. Okay? And equilibrium is the state where you finally reach the point where the number going in the forward reaction is equal to the rate of the reverse reaction. Okay? And so any chemical process that you allow to come to equilibrium, that's basically defined by saying that the forward reaction rate equals the reverse reaction rate. Okay? Now, the dilemma is how to write these two reactions. Okay? So this is key. The chemists use a double-headed arrow, and so if you see this backwards arrow, basically it's telling you to read this backwards. So if you're reading this backwards from right to left, it's saying that two HIs collide to make H2 and I2. Okay? The forward reaction is saying H2 plus I2 makes two HIs. Okay? And so that's what happens in this mixture of all these molecules. If you have an H2 and an I2 collide, well, if there's enough energy, they will make HI molecules. And if you have HI molecules in there, and if they collide with the right orientation and energy, then you'll get back H2 and I2 molecules. And eventually there will be some point where the forward and reverse reaction are the same. Now the other thing you can do is instead of starting reactants, you can start with HI molecules only. So what would happen there is, well, there would be no collisions between H2 and I2 because there are no H2 or I2 molecules. So the only reactions that can occur are when two HIs collide, because that's all we have. And so when two HIs collide, now we make a few of these. And so that means, even though we still have mostly these, and we're still converting most of the reaction is, rate is for the reverse reaction now, at least reverse of how we wrote it. So this is the other key thing, is there is no forward or reverse reaction except for our choice of what we call reactants and what we call products. Okay? See, if we start with HI only, we might want to naturally just call that HI the reactant. But we're just going to think of it as being the product for the way we wrote the reaction. All right, so if we have product only, then the reverse reaction starts occurring with no forward reaction because there's no reactants. And then as reactants are formed by the reverse reaction, then you'll see a tiny rate of forward reaction. And as this reaction reduces the number of HI molecules and builds up the number here, there'll be some point where the forward rate is now just as high as the reverse rate. And that's called chemical equilibrium. An analogy I like to use is like the restroom at a football game. And so you may have noticed there's probably a line. And so if the line is staying the same length, what that tells you is the number of people going in the bathroom is equal to the number of people coming out of the bathroom. That would be an equilibrium. So it's not the same people standing in line. That would be kind of creepy. But so in a chemical equilibrium, the reactions are constantly going. So that means H2 and I2 are constantly making HI. HIs are constantly reforming H2 and I2. Okay? It's just saying that there's no net change because the rate at which HI is being consumed is equal to the rate at which it's being made.